Great. Welcome back to another video segment on Python programming from beginners to programmers. So in this part of the video, we are going to move from the classroom discussion of data analytics on the pandas libraries, statistical calculations and functions. We have gone through that in the so-called classroom setting with my slides and all that. Now we come to this part on actually doing those performance and those calculations in Spider Lab. So join me over, run your Spider, and let's begin by defining our famous data frame, df6. And of course, not forgetting that we should always import numpy as np, import pandas as pd. So with this, we are then able to, first of all, make a copy of df6. Our original df6 was basically based on integers. So we're going to make a copy of it. And remember making a copy of it because data frame is a structured data type. And if we pass it to functions, pandas functions included, we don't know what pandas functions perform internally. It may make a copy, it may directly modify the passed in value. So if it directly modifies the passed in value, it will directly change our df6 here globally. So by making a copy, we are going to be very sure, double sure, that even if pandas functions internally modifies directly our df9, it's okay. You know, our source df6 is still intact. But we also have the need to modify column A just to have some variety of data type values. That means they're not all just integers. So we create this here. All right, so we have a list of data. We assign it to column A like this. And let's just print it out just to be sure what we're doing. So this is exactly what we saw in the classroom slides. And now we are ready to perform some data analytics. Okay. Um, Before we begin, let's just do a quick review. What does this command do? What do we get for df9n? So first of all, the base data frame is df9, which is what we see here. Then we perform a dot log, which is to extract, right? Extract where? Row, comma, column. So for row, it says everything. Okay, so we'll take 0 to 6. And for column, this is what I want to show you. For column, this interesting expression here may need a little bit of explanation. Okay, so this column here is actually trying to say, you know what, pandas, or actually dot log function, go and search for the beginning label in the column. Yeah, so it's going to find B and then range it over. That means keep going until you see the end label that is marked D inclusively. So it's going to extract B, C, D. So this colon means keep on going until you find. Okay, it's not necessarily B, C, and D. Yeah? So if I call it X here, it would still work. It will still be B, X, D, and all that. So it's not alphabetical or whatnot. So it's a very interesting notion because to dot log, it does make sense. There's some sense of sequentiality there, right? Because it's B followed by C. After that, C is following B, D is following C, and that's why the colon sequence notion makes sense. It's not discontinuous in that sense. So I just want to show you this quickly because it's also very useful. Okay, now let's try to do a lot of the usual stuff like the standard statistical analysis, which is to perform column sum. Okay, so I'll just directly put inside the calculation inside the f string here. So df9 dot sum Remember, that's not to add up all the numbers, but to do column sum, right? And then to do row sum, because x is equals to 1, then find the median for the column data, standard deviation column data, max, min, all right? So we should see the columns. Okay, that's a lot. So for dot sum, that's based on column sum. And for A, so we should see A, B, C, D first of all. But for A, it's a string, so it's going to concatenate the string values. Now, notice that if your A is a bunch of names, your final dot sum is going to be very bulky, right? So you might see this very fat A, and then your B, and then after that, big blanks, and then 32. So you might not want A to participate in there, even though it doesn't harm, it doesn't create error. Next, we have row sum. So our series output should be row indices. That's correct. Yeah. Then we have median, which is, well, if we don't specify, it is column based, right? So median here is going to be df9 dot median. The result skips column A. Why? Unlike dot sum, which can make sense out of string plus string, median has no sense in terms of bunch of x's, y's, and z's, right? So not meaningful. So it's not trying to squeeze a meaning out of it. Ignore column A. Likewise, for standard deviation, don't know what it means by calculating standard deviation of a string. So, right, so we skip that. For max and min, however, there is this ASCII code, right? So there is this converting string to at least the first character to numerical code, and then compare the code. So to the extent that z is greater than x, kind of correctly, we will return z. So max makes sense, and that's why A comes out. So you see that string is a little bit of a danger there, in the sense that if you kind of allow it to run across these statistical calculations, some calculations will have 4 rows, 4 results. Some calculations will have 3 rows, as in 3 results, right? Column-based results. So one has to be careful about that. Okay. All right. If you have questions so far, you can always go back to the slides, right? And we actually have seen the results already, but nothing beats actually, you know what? Actually seeing that it runs on its own. So let's go back to our lab, and now we perform the correlation. Okay, so to see what is going on in the correlation, we store it in df9c, and then let's take a look at the correlation after replacing the 1 with 0. But let's try it without. If we don't, then this is truly correlation table, right? So it's like B correlate with B, B correlate with C, which is mathematically the same as C correlates with B. So we just look at the upper triangular matrix here, right? So here it seems that 0.34 is the most positive correlation value amongst all the columns. Now we want to get rid of the ones. Assuming ones are only perfect ones only occur on the diagonal, then we can just do a dot replace. Okay, then the diagonals will be 0 out. The reason why it's 0 out is that then magnitude wise is the least correlated. We're not interested in seeing in the program telling us, hey, important, B and B are very correlated. You know, that is not interesting. So we are going to replace that. Now we want a means of automatically highlighting large positive column names, right? Large positive columns with large positive correlations to us. So the way it goes is this. Okay. Now, if I break it down this way, I think it should make it more obvious. Yeah. So internally, this, sorry, internally, this is going to be the filter. All right, and then we extract out a bunch of trues and false, right? Um, DF9C, do we have a DF9C? We have a DF9C. So DF9C equal to DF9C dot max, and it's going to highlight what is our DF9C. Okay, what is DF9C dot max? Like this, right? So the max for C here is 0, which is true, right? And if we want to extract it out, we would then use it against the base table of this. Okay, and then we perform a sum, and that is going to be this. And then you say, is it greater than 0? Because if it's greater than 0, then it is significant. Yeah, okay. So the maximum for each column, is the maximum for each column is being extracted out, and we do a final check and say, is it larger than 0? Okay, so because it's maximum, if all the values are very tiny and the maximum is just point 0, so all are zeros, then it's not interesting. But we finally do a greater than 0 to weed out anything that is zero-ish. Okay, and finally we get a series of B, C, D. In fact, we can just basically read off from here anything that's true, and we can always do a filter against the dot index, right? To against this particular mask. So that's what exactly we are doing. So we take out the index, and then we plonk it in as a mask to extract out the index. And then it gives us this rather intimidating package wrapping with an index and D type as if it's not ready. So what we do is just force a list, okay, to make it look like a decent Python list. Yeah. So this is indeed what we do here, and then we print out. So with the calls, we can also do a for column for C in calls, then perform the column to see, oh, which these are the interesting columns, right? What do we need to do about them? So then here on a silver plate are the names of the columns, or rather the factors, right, in our field survey, factors which are highly correlated, positively highly correlated. So next up, we have our discussion about cumulative sum. Where are we? Before we do that, oh, we also need our, yes, we should talk about describe, right? So next up is our describe. So let's do that. Okay, we are going to reset. I'm going to print a line across, do a copy again to reset our DF9, fix the DF9 to the letters again, and store the results of the data frame results of describe, right? So we print out and find the unique numbers, the unique number of unique items for each column, and return it as a series. So let's do that. Okay, so DF9D is the data frame created by dot describe, which tells us everything, right? All the basic statistics about each column, numerical column. And as I said, because DF9D is a particular data frame, so we can always use dot log to say, I want column D's standard deviation. Can you pass me that, please? Right? Oops, sorry. Column D. No, sorry, the other way around, because it's row, comma, column. So row, I want the standard deviation of column D.